And so we call a directory how we are really organizing our files in the system and how we are maintaining all the information related to all the files that we have in the system. And so the directory has to provide us efficiency. And so we have to find a file that we're searching for really quickly, and it has to give us naming convenience to the user. For example, we want to make sure that not two users, not two files cannot have the same name inside the same directory, and then two users, for example, can have the same name for different files. And then directory also should provide us some aggregation and grouping capabilities. For instance, putting all the Java programs in one directory and all the C files in another, and so on. And so there are different operations that we can execute on a file directory. Of course, searching for a file, creating a file, deleting a file, listing all the content of a file, and so on. And so there's different ways to organize the different directories into one global structure inside the file system, and we're going to name a few. The first structure is the tree structure. So as you can see, it's a tree-like file directory structure with every directory can point to multiple files or other directories that are in the next level. But every file except the root should have exactly one parent directory at the next higher level. And so we define the absolute path name of a file as a unique identifier to that file, and it's the concatenation of the directory and the file names leading from the root to the file. So if we look at this example, and so if we're considering this file, if this is file F1, then the absolute path to this file will be slash, right, going all the way to the root, right? And so it's going to be slash spell, slash mail, slash exp slash F1, right? So that's the absolute path name. But we can also define a relative path name, which is relative really to the current directory. So if we consider we are already in this directory, if this is our current directory, then if we just say exp slash F1, then this is a relative path to the same file, to F1. And so we can also define things as the file system provides us with the ability to refer to a parent directory using ... And so if the current directory is for instance it's prog, and then to represent F1, then we can go ... slash slash and then exp slash F1, right? So we're going back one level, and then we're going back into the directory that has the file that we're looking for. Okay. The problem with the tree structured directories is that, as we said, a file is only allowed to have one parent. And so another way to organize directories is using a cyclic graph structure. In this scenario, a file is permitted, or a directory is permitted, to have more than one parent directory. And so the way it does that is the file system gives us the ability to add links, right? And so we can add a link from one directory to the other, which means that one file is actually shared between two directories. And so in the acyclic graph directory structure, we have to redefine the meaning of the deletion of a shared file. Since we said that a file can be shared and pointed to by multiple parents, for example, here file F8 is pointed to by 3 different directories or parents. And so when we want to delete F8, what's going to happen is we have to first implement a new concept here called reference count. It actually represents how many directories are currently referencing or pointing to a file. And so when one of these parents calls the delete operation on the file F8, then the file itself is not going to be deleted, but what's going to happen is a decrementation or a decrease of the reference count. So instead of three parents pointing to F8, we're going to have only 2 when this parent calls the delete operation. So it's just the pointer that's going to be deleted, but not the file itself. So only when the reference count becomes 1, this means that this file has only 1 parent. Then when the deletion operation is called, then the file itself will be deleted. So the problem with acyclic graph directory structure is, since we said that every file is allowed to point to multiple parents at the upper level, then this may lead to cycles in our graph, and these cycles can cause problems like infinite loops when we are searching for any given file in our directory structure. And so to avoid that, we can use general graph directory structure. So in this organization, we only allow a single parent directory for any file or directory, but we do provide things like symbolic links or shortcuts. And so it is a directory entry that points to another file or directory, just like any regular entry, but the difference is when we want to execute a deletion operation, then the delete will only cause the link to break. We're only going to delete the symbolic link, but not the file itself. And so in this example directory structure, if we delete the root/a, then this will cause all of the files F1, F2, and F3 to be deleted. Now, if we want to delete the file F1 itself, right, then it has to be only done using the absolute path /b/e, right? But if we want to just print the file, then we can use any lead-in path to F1, including both the absolute path and the symbolic links, which are in green here. So we can use /b/e, we can use /a/d to F1, and we can also use /a/c/g/j to print the file F1. And so to protect a file, there's different ways to do that depending on what operating systems we're talking about. And so under Unix, you can use things like access lists and groups to protect the access to the file. And so there are different modes of accesses, namely the read, write, and execute under Unix. And so in Unix Linux systems, we define three classes of users of a file: the owner of the file, the group, and the public. And so we can define the access rights to that file depending on the class of the user that we're talking about. For example, here we can give the right to read, write, and execute for the owner, so the full access to the owner, and we can only give the right to read and write to the group, which so the user has the ability to create a group that only specific users belong to. And then when it comes to anyone else that does not belong to that particular group, we can just give it the execute right? So 111 is 7, and then 011 is 6, and 100 is 1. And so if we give the 761 access right to a file, so to change the access rights, we use the chmod command under Linux systems, and this is the name of the file. So we want this file to be only executed by the public and read and written by the group, and read and written and executed by the owner of this file. And so, as we said, files can have multiple attributes related to them to represent all the related information to that file. And so things like the ID of the file, which is unique to that file, and it is used internally by the file system to represent and identify that file, and it's not really visible to the users. What the users can see is the name of the file, which is really those ASCII names that we see, like myfile .txt or semaphore.txt or .c and things like that. And so other attributes will be the type of the file, the location, the size, the access, access list, and so on. And so a question here is, where do we really keep all these file attributes, right? And so one approach is to keep all the attributes together with the file name in one location inside the file directory. So if we think of the file directory as an array, then when we put the entire attributes of a file together in one array, and then the next file and the next, this will make the directory really long, and it will slow down the searching process, right? And so another alternative is to only keep the file name in the directory, in addition to a pointer that points to a separate data structure that has all the other file attributes. Okay, we're going to talk about that data structure in a second. A third approach is to keep the file name and release some of the critical attributes that we want quick access to, and then a pointer to all the other attributes that are kept in a different data structure. Now, what's that data structure? That data structure is called a file control block, right? Remember, just like a process control block, here it is called a file control block. So it is that data structure that is associated to every file, and it has all the relevant attributes to that file. Okay, and so we can save that FCB apart from the directory and only keep one pointer to it inside the directory as an entry. And so in Unix and other operating systems, the FCB or the file control block sometimes is called the inode. Therefore, when is it preferable to keep only the file name and a pointer to the FCB in the directory instead of putting all the attributes together as entries in the directory? Is it when the file name is very long? Not really, because the file name will always be there as an entry to the directory, right? It doesn't really matter. Is it when the attribute lists are very long? Yeah, actually, when we have lots of attributes, it is really preferable to move them all to the FCB and only keep a pointer to them as an entry in the directory. Does it matter when we have the number of files per directory really large? It does, actually. When we have lots of directories, this means that the array will be really large, and then the search will slow down, and so it is preferable in this case to have just pointers to the FCB. What about when the file header is long? We don't really care about the file header. It is not part of the directory entries. It is that first part in the file itself that represents some information about the file, like the magic number and others.